We're getting into something new today. So the new topic is internal loads and beams. And a beam is a long, slender body. But this is the key thing for when you hear beams. It's intended to support at least one non-axial load. So if you have something like this and the loads it supports are like this, you know, F1, F2, F3. If it's designed to support things like that, that's not a beam. But something like this is a beam. So the key thing is that it's not just in tension and compression. It has other things going on that would tend to bend it. Okay, so internal loads. You can think of this as the first step toward determining if and where an object will break. At the start of the class, I gave a tree of all the things in mechanics, including dynamics and deform and stuff. And the one side of that tree was all the classes that are asking the question, is this thing going to break, and where and how, you know? And so this is kind of the beginning of that question. And so here is sort of the motivation for this. Okay, so imagine you hold like a stick between your two hands. And bend it. Okay. If you draw a free body diagram of that stick, it would look something like this. You have the upward force from your thumbs. Call that F1. And then you have the downward force from your fingers. Call that F2. Okay. You with me on that? And if all you're looking at is the external loads, you would tend to think, like your first thought would be like, okay, if someone asked you, where are you worried about this thing breaking? you'd say, well, there's the four forces, so pick one of those, you know. So in your first thought, you'd think that this stick is most likely to break at one of those external loads. But then, you know, you've done this with sticks and pencils and whatever, and that's not where it breaks. It'll actually break in between your two thumbs. Okay, so like what's going on with that? Well, the question isn't really the forces that the outside world is applying to the thing. The question is the forces that you're requiring the thing to apply to itself at different locations. Okay. So what matters is where large loads are applied to the material by the surrounding material, you know, by the other parts of the stick, in order to maintain equilibrium. And those are internal loads. So internal loads are the loads that are applied to the material by surrounding material, adjacent material. You can think of, I never used to play this, but I've seen it in movies, this game, Crack the Whip, where you get a bunch of people holding hands. And you start spinning around, you know, and eventually somebody loses their grip and everyone falls down. It's fun for everyone. Well, if you imagine all these people being the same strength, because this is an analogy for like metal or whatever, it's the same strength everywhere. This line of people is going to break into two at the location where one of those grips is being asked to, you know, being required to be a higher force than the other ones, you know. And that's the idea. If you think of that as an analogy with internal loads, it's like that. You're asking that metal to hold on to it, to the surrounding metal. And if when you require it to apply a really big force, eventually it fails, you know. So it's the same thing as asking people to hold on to each other's hands until one person just can't do it anymore. The force at that location that's required to keep the thing together just isn't sustainable. Okay, so I'm going to start with an example. This principle is pretty simple. So let's say we have a beam and the loads on it. I'm not going to show any joints or anything. I'm just going to give all the forces right to start with. Say these are all newtons. That's in equilibrium if you did the rigid body Newton's laws. You get that this is in equilibrium. And let's say that we want to figure out the force here at that red line that's applied to the piece on the left of that line by the piece on the right. And I'll give you some dimensions. So let's say that the whole thing is a meter long. This is a quarter. This is a quarter. This is a half. And we want to know what are the loads applied to the material to the left of the red line by the material to the right of the red line. Okay, so how are we going to do this? You know, in order to calculate external loads on anything, you draw the free body diagram, you write out the table or whatever, and use Newton's laws to calculate the forces and couples. Well, this is all one body, you know, but we can isolate any piece of that body we want. So what I'm going to do is just choose as my chosen body all of the stuff to the left of that red line, and I'm not going to include any of the stuff to the right. And then all of the forces and couples that are applied at the red line by the stuff on the right now are external loads to what I'm considering, okay? So my free body diagram, okay, I'm going to isolate the material to the left of the red line. So here's what the free body diagram looks like. Not like that. So there's what I'm isolating. I'm going to use this color to show all the stuff I'm not isolating. Okay. And that means that, so what's included? I'm including, so this 500 Newton force is on the body. This 1,000 is over here somewhere, so that's not included. This 500 is over here, so that's not included. Okay. What other loads are acting? Yeah, that's exactly right. So what we're going to do is treat the connection between those two things as a fixed joint. Okay. And so what are the loads applied by a fixed joint? You have a full vector of unknown force. I'll call that R. And then a couple, an unknown couple, call that M. And now we can write out the table because this is just a rigid body statics problem. I'll use this as the about point. And so for the 500 Newton force, the rho vector is 0. The force vector is 0, negative 500. The moment is 0. Then for R, to get from the about point to where that force is applied, it's 0.250 is the rho vector. The force is Rx, Ry. And so the moment is 0.25 Ry. And then the last thing is that moment it's a couple, so we don't care about these things, and we'll just write it as M. And now Newton's second law comes from the second column. The moment equation comes from the third column. So Newton's second law says Rx, Ry plus 0, negative 500 is equal to zeros. So right away we can calculate that this R vector is 0 for X, positive 500 for Y. And then the moment equation says M plus 0.25 Ry is equal to 0. And so M is equal to negative 125 Newton meters. Did I do that right? Yes. So that all makes sense, right? The only thing that we did that's sort of new is just choosing a part of a body to isolate. After that, this was a really simple rigid body calculation. So you can think of that as telling you the internal loads at that red line. There's one complication that we have to deal with. So except for one thing. We would like these internal loads to tell us something about so the calculation we do, we'd like it to tell us something about what those internal loads are at that red line, independent of how we calculate it, okay? And there's no reason that I had to calculate the force on the left piece by the right piece, right? I could have calculated the force on the right piece by the left piece. That seems just as reasonable a way to calculate the internal loads at that line. But what would I get for the answers if I had, instead of isolating the little left piece, I'd isolated the big right piece? Yes, it's a Newton's third law thing. You know, instead of calculating the force on the left by the right, we'd be calculating the force on the right by the left. So we would have gotten that the force was 0, negative 500, and the couple was positive 125. Okay, and so we want to deal with that. It's just going to be a sign convention thing. It's not hard to deal with, but we want to make it so however we do this calculation, we get the same answers. Okay. So if we had done this calculation by isolating the right piece, bless you, Newton's third law says we would get opposite answers. So we're going to choose a sign convention that deals with this. We're going to define a sign convention that makes those two approaches agree. And the sign convention we're going to use is a little odd, but people find this long before I was ever invited to any meetings about it, so I just got to do it. So a force like this is called T. That makes sense, because if T is positive, that thing's in tension. If it's negative, it's in compression. Okay, now here's where it gets a little weird. We're going to call this capital V the shear force, and a positive value of V is a downward force. I don't know why, but that's how it is. And then back to sort of the sign we would expect, a couple capital N. And the thing that makes the left agree with the right is if you're dealing with the other, coming from the other direction, a positive value of T is this. A positive shear force is up, and a positive couple is in. And so these are called the tension, the shear force, and M is called the bending moment. Okay, so I wanted to just show you that so sort of the take-home message of this is the basic idea is we're isolating just a piece of a body. We're treating the connection to the rest of the body as a fixed joint, and then calculating those reactions. But because of the indeterminate thing with the signs, we also define a new sign convention that's a little bit haywire with the downward shear force, and that's what sort of hides the fact that all it is a fixed joint. But all it is a fixed joint. That shear force, you can think of that as like, it's called a shear force because that's the kind of force that, like if you're using scissors on something or whatever, that's the kind of force that the scissors would be applying to it. Okay, so let me do that same calculation again, but this time I'm just going to use the sign convention, the internal load sign convention. So this is the same, but using T, V, and M. And again, I'm not going to do this all the time, but just for now, I'm going to do this a few times. just hopefully to help you kind of keep your brain oriented on where we are on this beam. So the internal loads are T, V, and M. And again, this is a rigid body problem, so we can write out the table, rho, F, M. And I'm going to always do these calculations with the about point at the left end. You don't have to. It's just like any other rigid body statics problem. But for these, you'll see that you'll always want to use that same point. And this upward force is 500. Okay, so that 500 Newton force, the rho vector is 0. Force vector is 0, 500. Dang it. Okay. So this is negative. And the moment is 0. And now we'll go to the tension. The rho vector is 0.250. The tension vector, so I think the easiest way to think about these is the arrow gives you a unit vector, and you're multiplying that by the variable. So what's a unit vector in the direction of that arrow? 1, 0. Yep, it's just in the positive x direction. Okay, and so 1, 0 times t is t0. Cross product is 0. Now the shear force is where this helps you sort of keep yourself from getting confused. So the shear force, the rho vector is 0.250. What's a unit vector in the direction of that arrow? 0, negative 1. And 0, negative 1 times v is 0, negative v. And so that cross product is negative 0.25 v. And then the last thing is the bending moment. We don't care about that stuff. And it's just m. So now Newton's second law says 0, negative 500 plus t0 plus 0, negative v is equal to zeros. So t is 0. This thing is not in tension or compression at that point. V is negative 500. And now the moment equation says negative 0.25 v plus m is equal to 0. So m is equal to 0.25 v. Plug in our value of v, and you get m is equal to negative 125 Newton meters. Yep.
So are these, additional forces the reason why we didn't choose the point of action at the...
No, that is going to be for when you'll see that the next thing we're going to do is not calculate the internal loads at a single line like that, but we're going to come up with internal loads as functions of x as you move along. And this is going to help you keep your head straight for that. So there's no reason you have to do it, it's just because it's going to make the math simpler. And that's going to be true later on too. You could choose any about point you want, but you won't want to,
When we did the force table for V, and you said that down is the positive direction?
Yeah.
Why did we put it as negative?
Okay, because you can always think of a free body diagram with known directions like that. You can always think of the arrow as a unit vector multiplied by that variable. Okay, so or by that value. So in this case, I mean, you're used to thinking of that as 0, -500. But you could also think of that as 0, -1, the arrow, times 500, and you get the same thing. But it's more confusing when you get to variables. So you're doing the same thing here. This is 0, -1. You're multiplying it by v, so you get a 0, -v vector.
Okay, that makes sense.
I wanted you to notice something. So up until now, for rigid body statics problems, we've always used that table. Okay, but all of these beams we're going to do are going to be horizontal. And there's a much quicker way to do these calculations if you're dealing with 2D horizontal members like this. So notice there's a quicker way than the table for horizontal beams like this one. So first, just write out the forces. The table usually, I mean, doesn't help you too much with the forces. It's nice to have it in that column, but really the table is there for the cross products, But go up to that free body diagram and just think about it. Think about it this way. Since this is horizontal, all you're doing is multiplying the distance from the about point to whatever vertical force you're applying. Horizontal forces don't produce any moment, right? And so, so the moment produced by V, to get that, it's just going to be this length, 0.25, times V. And then you have to think, is it positive or negative? And you just think that by, think of that as a hinge and just ask yourself, if you whack the end of this with a hammer downwards, would it rotate counterclockwise or clockwise? In this case, it's clockwise, okay? So it's negative. And it's just a way, I mean, you can always do the table, but this is a lot faster for horizontal things. Because the thing that makes other things more complicated is you're not always going to have perpendicular row vectors and force vectors. In this case, our row vector is just always perpendicular to the force vector. So moments are only produced by vertical forces and couples. Those are their own thing. Yeah, like if you're doing the math of the beam that you're doing is actually standing up like a statue or something, and you're doing the calculation, you mean? In that case, like turn your head like this and do the problem like it's horizontal. You know?
Why is it different?
That's just, you could do it vertical, but you just want to do it all the same way. And since, 50 years or 100 years of people have done it horizontal, we'll just keep doing it that way, not rock the boat. But there's no problem with, you could do it vertical.
Either this or that?
Yeah, right.
So it has nothing to do with like gravity?
Nope. Right. You'd have to consider, in either case, you'd have to consider gravity the way it's pointing. But I guess I ignored it in this problem. But we'll see gravity in these. Okay, so moments are only produced by vertical forces. Multiply the force to the distance from the end. Because the end is the about point. And then the sign is just by inspection, just thinking about which way it would rotate if you applied that force. So I'm going to just redraw this free body diagram we had. We have the downward force of 500. Then we have T, V, and M. So for the moments, this is the about point. This distance is 0.25. Bless you. Okay, so for the moment equation, the 500 acts through the about point. There's no moment there. 0.25 times V, that's plus or minus, right? Now, by inspection, you think about which way it's going to rotate. It's clockwise, so take the negative. And then plus M is equal to 0, and you get the same thing. All right, I want to show like the same simple beam, but with cuts in a couple different locations. And I want you to notice something about it. Okay, so now consider the same beam isolating the left end from 4 different locations. Okay, so here is the whole beam. Okay. And the places I want to make this cut are close to the left end, like that. I'm going to call that cut 1. And let's make this distance 0.01 meters. Okay. And then I want to do a cut here, close to the 1,000, but on the left side. I'm going to call that cut 2. And that distance is 0.01 again. And then I want to do the same thing here, just 0.1 away on the other side of that. Are you with me on all this? And then I want to do a distance of 0.01 meters from the end. So those are the 4 places we want to do this calculation. Well, I'm not doing a calculation. I'm just going to draw the free body diagrams. But I want you to notice something about these free body diagrams. So free body diagram, where the right end, where this piece ends at 1, looks something like this, right? It's just a little stub of a, and so what loads are acting? There's the 500. We haven't gotten anywhere close to this 1,000 Newton force. So now we just have the internal loads, T, V, and M. Okay. And now I'm going to draw a free body diagram where I'm isolating the whole beam, starting all the way at the left and ending at 2. Okay, so free body diagram for that cut 2. There's the downward force of 500. What about the 1,000 Newton force? No, we're still not there. So there's no 1,000 Newton force, and the only thing we have that we haven't drawn yet are the internal loads, T, V, and M. And now free body diagram where the right end is at that 0.3, okay? So this is only 0.02 meters farther as a beam than the last one we did. Let's see. And there's still the downward force of 500. Now what about the 1,000 Newton force? Now it is in there. It's like here somewhere. Okay. And then we have the internal loads, T, V, and M. And then the last one, where the right end is going to go all the way to that number 4. We have the 500. Do we have the 1,000? Yeah. Now it's about halfway along this piece that we're isolating. Do we have the other 500? Nope, we're not quite there. And so now the only things we have are the internal loads. So notice that these two are, qualitatively similar. The lengths aren't the same. That is a long word. I'm not writing that again. And then these two are the same. Okay, and it doesn't have anything to do with like them being close to the same length. This number 2 and number 3 are actually the closest to the same length, but they are not qualitatively similar. This one has a force in it that this one doesn't have. Okay. And so the next thing that we're going to do next class is we're going to use this idea of these qualitatively similar pieces in order to figure out how to calculate internal loads as functions of x inside for each one of those like sections that are qualitatively the same. But you can see that something is going to happen every time we have a point force or a point couple, or there's some other things that can happen. But there are going to be big chunks where we can treat this piece that's 1 centimeter long and this piece that's 49 centimeters long mathematically the same. Yep.
When we get further into this, are we still going to be able to treat distributed loads as like a point force?
Yes, but it's going to get complicated because, so think of, okay, so say you have this body and you have a support here and a support here and a distributed load like this. Okay. And now let's say that we make our cut somewhere. So we're just isolating this piece. We're ignoring this piece. Okay. So we don't see this force. We do see this one. We see the distributed load to there, but we're ignoring a whole bunch of the distributed load. And so we're going to have to figure out how to deal with that. But once you figure out, and then this will have the internal loads too. But once you figure out how to represent the part of the distributed load that you do have on your member, then you can represent that as a point force. You just have to be careful that you're not dealing with any of that stuff that's not acting on your cut. So we'll get to that pretty soon. But okay, so next time, the thing we're going to do is talk about how to calculate, use this qualitative similarity between certain cuts to express internal loads as a function of x. Okay, that's all. Have a good MEA. Don't come to school tomorrow or Friday.